Welcome everyone to where we are putting together solutions for those math and science topics that we are getting problems with. Today we will be looking at proportionality in mathematics and its connections to other sciences such as physics and chemistry. This is our first video in this mini-series, so feel free to like the video and add comments in the description down below, or post which topic that you may need help in so that we can make a video for you. When two variables are proportional, it means they're related to each other by a fixed ratio. There are two types of relations. One, when one variable increases as the other increases. That means as x goes up, y goes up. This is called directly proportional. The other type of relation is where one variable decreases as the other increases. So x goes down and y goes up. This is called indirectly proportional. We will now look at a directionally proportional example with a seesaw and boys and blocks. At present, there is nothing on the seesaw, so the seesaw is balanced. Now that we add two blocks on the right hand side, the seesaw will go downwards in a clockwise direction until it hits the ground. In order to balance it, we will now add a boy on the left hand side. As you can see, it comes back up and it is now balanced. So the boys and the blocks are equally distanced apart from the fulcrum or the pivot, and it tells us that the boy has the same weight as two blocks. We now continue the same example with the seesaw, but we will be adding 4 blocks on the right hand side. As you can see, the seesaw will go down in a clockwise direction, just as before. Now we will add one boy on the left hand side. Will the boy bring him back up? No. And that is because the boy only weighs 2 blocks, so that they cannot balance each other. As we continue the example, where the seesaw has 4 blocks on the right hand side, causing it to go down, and one boy on the left hand side, which doesn't cause it to come back up. We now add a second boy to it, and as you can see, the seesaw now levels itself and it is balanced. This tells us that 2 boys has the same weight as 4 blocks. So if we look at the table, when we had 0 boys, there was 0 blocks for it to be balanced. When there was 1 boy, there were 2 blocks for it to be balanced. And now there were 2 boys, then you require 4 blocks for it to be balanced. Let us now look at the same situation, and we are plotting the information onto a graph. We recognize that as the number of boys increased, the number of blocks to balance the seesaw also increased. So if we plot the graph, plotting on the x-axis boys and on the y-axis number of blocks, then we can see our first point will be at 0 boys requires 0 blocks for it to be balanced. And then 1 boy required 2 blocks for it to be balanced. And 2 boys required 4 blocks to be balanced. And we can extend the graph and see for 3 boys how many blocks do we need, and for 4 boys same thing. This is a straight line graph, better known as a linear graph. But it's a special one. Since it is passing through the origin, it is called directly proportional. If we look at a second graph where it is also a straight line, but it does not pass through the origin, then we will just call that a linear graph. Let's look at the same question numerically. If you recall, for one boy, there were 2 blocks that were required to balance it. For 2 boys, 4 blocks. For 3 boys, 6 blocks. So we can write a little formula. Boy is equal to some factor times blocks, where this factor is a constant. So boy will be equal to a constant times blocks. This means that as the number of boys go up, the number of blocks go up. So we can say that boys are proportional to the number of blocks. And this little sign here shows proportionality. Other numerical examples include, for a formula, f is equal to k times v squared, where k is a constant. That means f would be equal to a constant times v squared. So, if f increases, then v squared increases. So we can say f is proportional to v squared. And for the last formula, v is equal to 4/3 pi r cubed, where 4/3 pi is a constant. So we can rewrite it v is equal to some constant times r cubed. So if the volume increases, v, then r cubed increases. So v is proportional to r cubed. We are now going to do a second example, which is based in chemistry and mathematics. This is the pressure law. The law says that the pressure of an ideal or perfect gas at constant volume is directly proportional to the absolute temperature. So we're giving a table where we have the pressure at 1000, the temperature will be 400, and we are required to find out T1 when the pressure is at 800 and P2, pressure at 600. So how do we go about finding this? Using a graphical method. Now what we must remember, since it says it's directly proportional, this means that there's a graph and the graph goes through the origin where the pressure will be 0 and the temperature will be 0. So we already know one point. Now there's a second point they gave us. 1000 is the pressure and 400 is the temperature. So we have 2 points. And since this is a directly proportional graph, then we can draw a straight line through those 2 points. Now we can look at the pressure at 800, and from there on the y-axis draw a line going horizontally until we hit the blue line, and then come down vertically and read off our T1 value, which works out to be 320. And similarly, to solve for P2, we know the temperature is 600. So we go on the temperature axis, which is the x-axis, and draw a line of 600 straight up until it hits our blue line, and then we go across horizontally to hit our pressure axis, our y-axis, and that tells us that the pressure there is equal to 1500. We are now going to repeat example 2, the pressure law, but using a numerical method. Remember, it is a straight line graph, so y is equal to mx will be the general formula for that, since it is passing through the origin. Now we can replace the y and the x with p and t. So p is equal to kt, where p is for pressure and t is for temperature, and k is our constant. Now we have 3 unknowns here, and if we look at the center values, we are given p and t. Since we know p and t, we can now substitute into there to find k, the constant. So p is equal to kt, and we substitute in p is equal to 1000 equals k times 400. And if we want k alone, then the 400, which is multiplying on one side, becomes division on the other side. So 1000 divided by 400, so k is equal to 2.5. Remember, for this entire question now, k is going to remain 2.5. It's a constant. So the formula now becomes p equals 2.5 times t. And if we are going to solve for T1, we can now substitute P as being 800 equals 2.5 times T1. So T1 is equal to 800 times 2.5. So that works out to be 320. The same answer we got using the graphical method before. And finally, P is equal to 2.5T, and we can find for P2. So P2 is equal to 2.5 times 600, which works out to be 1500, just as we did in the graphical method. We will now do a third example in which the formula is given F equals K times V squared. Now remember, K is a constant, and from the table there, we are given in the first set of values the force to be equal to 75 and the velocity to be equal to 2.5. So if we know F and V, we can now substitute to find for K. So F is equal to K V squared, and F is equal to 75 equals K times 2.5 squared. So we can work out 2.5 squared, and that will give us 6.25. And then we will divide, so we get 75 divided by 6.25, and we solve for K to be equal to 12. Now for the rest of the equation, K is a constant of 12. So the formula now states F is equal to 12 V squared. Let's substitute for M and 4 into it. So we get M is equal to 12 times 4 squared, which is equal to 12 times 16. So M is equal to 192. And finally, F is equal to 12 V squared is our formula. And F is given as 2880. And we don't know N. So we can substitute. 2880 is equal to 12 times N squared. So 2880 over 12 is equal to N squared, which works out to be 240 is equal to N squared. So N is the square root of 240, which is equal to approximately 15.5. Let's do a final example here with the volume of a sphere. Remember, V is equal to 4/3 pi r cubed, but 4/3 pi is a constant, so we can rewrite it as V is equal to K r cubed. Now using the table there, if you recognize V, K and R are 3 variables, but on the last line of the table, V and R are given. So if we substitute into there, we should be able to find K. So V is equal to K r cubed. 54 is equal to K times 3 cubed. So now that we've substituted, there is only one unknown on the line, which is K. So we should be able to solve for that. So 54 is equal to K times 27. 54 over 27 is equal to K. So 2 is equal to K. Hence, from now on, V is equal to 2r cubed, because K is equal to 2 for the rest of the question. Now, we can substitute to find for A. When V is equal to A, the radius is 5. So we can write A is equal to 2 times 5 cubed, which works out to be 2 times 125. So A is equal to 250. And finally, V is equal to 2r cubed, and we'll substitute to find B. 2000 is equal to 2 times B cubed. So 2000 over 2 is equal to B cubed. So 1000 is equal to B cubed. And we carry the cube across, so it will be cube root of 1000. B is equal to 10. We now have an exercise for you to practice with 4 questions for you to find the 2 unknowns in each one of them. Please stop the video and try and work out the 4 questions. When you are finished, restart the video and look on the next slide for the solutions. These are the solutions for the 4 questions that were given before. Thank you for joining us with our part 1 video, and feel free to hit the link and go on to the second and last part of the series, where we will be investigating indirectly proportional. Don't forget to add in the comments if you need any help in any particular topic, so we can make a video for you, and don't forget to subscribe. Bye.